All right, let's jump right in. Today, we're not just solving one little problem, we're actually building a complete workshop. We're going to assemble the ultimate toolbox for dealing with linked lists, and we'll fill it with some seriously powerful techniques to handle the most common challenges you'll face. So, let's get to it.
Let's be real for a second. Linked lists can feel like this tangled up mess of pointers and nodes, right? But what if you had a set of reliable tools where each one was perfectly designed for a specific job? Well, that's exactly what we're going to do. We're going to build that toolbox so the next time you're up against a linked list problem, you'll know exactly which tool to grab.
First up, every good toolbox absolutely needs a cleaner. This tool is all about tidying things up. We're going to tackle one of the most fundamental tasks out there, getting rid of duplicate values from a list to make it nice, clean, and unique.
So, what's this cleaner tool actually do? Well, you can see here we're starting with an unsorted list that has some repeated values floating around. Our goal is to process it so that every number shows up only once. But, and this is the really crucial part, notice how the final list keeps the original order. The first time we see a 12, it stays. The first 11, it stays. The second 12, that's the one that gets cleaned out. Okay, so the first way we could build this tool is probably the one you'd think of first. It's the straightforward brute force method. We use nested loops. So you'd pick a node, let's say the first one with the value 12, then you run a second loop all the way through the rest of the list, hunting for any other 12s and kicking them out. Then you just move to the next node and do it all over again. It definitely gets the job done, but you'll see it has a pretty big hidden cost.
Now for a much more slick approach. Instead of scanning the list over and over again, we can use a hash set, which kind of acts like a short-term memory. We just walk the list one single time. For each node we visit, we ask our hash set, hey, have I seen this value before? If the answer is yes, we know it's a duplicate and we remove the node. If the answer is no, we just add the value to our memory and keep on moving.
And this slide right here perfectly shows the trade-off. Think of time complexity as the price you pay in processing time and auxiliary space as the cost in memory. The nested loops, they're really cheap on memory, but man, are they expensive on time. The hash set approach completely flips that. You pay a little bit more in memory to get this massive discount on time. And trust me, for large lists, that's a trade you're going to want to make every single time.
All right, tool number 1 is in the box. Now let's grab our next tool. We'll call this one the matchmaker. This one is specifically designed to work with two lists at the same time, finding exactly what they have in common.
The goal here is super clear. We're given two lists that are already sorted from smallest to largest. The matchmaker's job is to create a brand new list that contains only the elements that show up in both of them. So in this example, you can see that 2, 4, and 6 are the common values, so that becomes our result. Pretty straightforward, right?
So how do we do this efficiently? Well, because the lists are already sorted, we can use this really clever two-pointer technique. Think of it like a synchronized dance. We start with a pointer at the very beginning of each list. If their values match, perfect. We add it to our result list and both pointers take one step forward. If they don't match, we only advance the pointer with the smaller value, basically letting it try to catch up. We just keep doing this little dance until one of the pointers reaches the end of its list. It's simple, it's elegant, and it's super fast.
Okay, now for a real powerhouse. This is a tool that might seem simple on its own, but it's actually the fundamental building block for one of the most famous sorting algorithms in all of computer science. Let's add the sorter to our growing toolbox.
The main job of this tool is to partition a list. We pick a pivot value, let's call it x. The goal is to completely rearrange the list so that all the nodes with values less than x come first, then all the nodes that are equal to x, and finally all the nodes that are greater than x. Now, here's a key detail. We have to preserve the original relative order inside each of those three groups.
So how in the world do we pull this off? Well, the strategy is surprisingly simple. We're going to create 3 brand new empty linked lists that will act as our buckets, one for less than, one for equal to, and one for greater than our pivot.
Here's our starting line. We've got the original list up top and our 3 empty buckets waiting at the bottom. Okay, let's start sorting. For this example, we'll say our pivot value is 3. So we grab the first node from our list, which has a value of 1. Since 1 is less than our pivot of 3, it goes directly into our less bucket. Easy enough. Next up is the node with the value 4. Well, 4 is greater than our pivot, so it gets moved into the greater bucket. And we just keep this process going, taking one node at a time and placing it into its correct bucket. And after we've processed every single node from the original list, this is what we're left with. Notice that the less list has 1, 2, and 2, and they're in the same order they appeared in originally. The equal list just has our pivot, 3, and the greater list has 4 and 5. 3 perfectly partitioned lists. And now for the final, really satisfying step. All we have to do is connect them. We link the tail of the less list to the head of the equals list, and then we link the tail of the equals list to the head of the greater list. And just like that, we have our fully partitioned result, a seriously powerful technique.
Okay, we've built 3 really solid tools so far, but now it's time for the grand finale. We're going to see how that last tool, the partitioner, can be used to build a master algorithm. This is where everything we've done comes together. And this is the key question, isn't it? We've managed to divide our list into 3 groups around a pivot. That's cool. But the less than and greater than groups are still all jumbled up internally. So how does this actually help us sort the entire thing?
The answer is a really elegant process called recursion. The recipe for quicksort is basically this. First, pick a pivot. Second, use the partition tool we just built. This is great because it puts the pivot in its final sorted position. And third, this is the magic part, you simply run quicksort again on those 2 smaller, unsorted sublists on either side.
Let's see this in action really quick. Here's a brand new, completely unsorted list we want to sort out.
So, if we pick 5 as our pivot and run our partition tool, this is what we get. The 5 is now locked into its correct final spot. It's not moving. To its left, we have a little sublist of all the smaller numbers, and to its right, a sublist of the larger ones. Now we apply the exact same logic to those smaller lists. We'll partition the left list and partition the right list. We just keep breaking the problem down into smaller and smaller pieces until every single element is in its final sorted position. And there you have it. Your linked list toolbox is officially stocked and ready to go. You've got the cleaner for getting rid of duplicates, the matchmaker for finding common ground between 2 lists, and the sorter for partitioning. And most importantly, you now know how to use that sorter recursively to build the master algorithm, quicksort. These tools can solve a huge range of problems. They really can. But the world of data structures is massive. So I'll leave you with this question. Based on the challenges you've personally faced, what's the one tool you would add to this toolbox? Thanks for watching.